This is an example of a hypothesis test for a population mean when sigma is unknown. A light bulb manufacturer guarantees that the mean life of a certain type of light bulb is 750 hours. A random sample of 25 light bulbs has a mean life of 745 hours and a standard deviation of 60 hours. Assume the population is normally distributed. At a level of significance of 0.02, do you have enough evidence to reject the manufacturer's claim? The conditions are met to use the t-test. Because we're told to assume the population is normally distributed and our sample size is less than 25, we can go ahead and find our standardized test statistic, which will be a t-value. The claim from the manufacturer is that the mean life is 750 hours. So as a mathematical statement in terms of mu, that's going to be mu equal 750, and that is the manufacturer's claim, so that makes the claim the null hypothesis. There's no sense of direction implied here. The alternative will be not equal to 750. Our standardized test statistic follows the t-distribution, and the formula is x bar minus mu divided by the sample standard deviation over the square root of n, the sample size. We're given that the sample mean is 745, the sample size is 25, and the sample standard deviation is 60. Plugging those pieces into the formula, the standardized test statistic is negative 0.417. The t-distribution is bell-shaped, a little shorter with heavier tails than the z-distribution. And to find the critical values, I have to keep in mind that this is a two-tailed test, so our level of significance, 0.02, needs to be divided in half, and there'll be 0.01 amount of area in each tail, each area of rejection. Using the t-table and reading over to an area in the upper tail of 0.01, because that is half of alpha, and down to 24 degrees of freedom since the sample size is 25. The upper critical value is 2.492. So that makes the lower critical value by symmetry negative 2.492. If you want to find the critical value using your inverse t distribution in the calculator, it's fairly easy to do. If you have a newer TI-84, go to your distribution menu, select inverse t, and you need to input the cumulative area to the left of the critical value. So I can put in an area of 0.01 to find this lower critical value. The degrees of freedom is 24. And you'll see that it outputs that negative critical value. And by symmetry, I know my upper critical value will be positive 2.492. The test statistic is placed well in the fail to reject region, so I know my decision is to fail to reject the null. So I could circle the null and see that I also circled the claim because I'm failing to reject the null, and the null is the claim, to answer the question, do you have enough evidence to reject the manufacturer's claim? The correct way to answer that is that there is insufficient evidence to reject the manufacturer's claim that the mean life of the light bulb is 750 hours. To find the p-value, you definitely want to use technology, as the t-table is limited. To find the p-value from the TI-84, go to your stat menu, over to tests, and option 2 is the single sample t-test. I've already inputted the information. You'll need the null value, the sample mean, the sample standard deviation, the sample size, and make sure you choose the correct direction of the alternative. In this case, it's not equal. Otherwise, you will get the incorrect p-value. After pressing calculate, you'll see that the standardized test statistic is the same as I got when I did this by hand. And here's the corresponding p-value. The p-value is 0.681. And when your p-value is greater than or equal to your level of significance, the decision is to fail to reject the null, which is the same decision as we got when I used the critical value method.